25.2 Calculating Capacitance. In this lesson, we will explore the methods for calculating capacitance across various geometric configurations. We begin with an overview of the physical units and the charging process that occurs when a capacitor is connected to a power source. We will then derive specific formulas for the capacitance of an isolated sphere, as well as the more common parallel plate capacitor. Beyond these basic shapes, we will examine the properties of cylindrical and spherical capacitors, which are often found in specialized applications like coaxial cables. Finally, we will introduce the standard circuit symbols used to represent capacitors, batteries, and switches in electrical diagrams. Understanding these fundamentals is essential for analyzing how energy and charge are stored in electronic systems. When we look at physical capacitors in the lab or in consumer electronics, they are typically labeled with units of microfarads, abbreviated as lowercase m, f, or picofarads, denoted as p, f. You may occasionally encounter the older notation double m, f, which is equivalent to picofarads. A critical pitfall to avoid is confusing the italicized letter C, which represents the variable for capacitance, with the non-italicized C used for the unit coulomb. To charge a capacitor, we use a battery as a source of potential difference, or voltage. When the plates are connected to the battery, an electric field is established in the wires, driving the movement of electrons. This process continues until the potential difference across the capacitor plates exactly matches the potential difference of the battery. At this point, the system reaches equilibrium and the flow of charge stops. Let us take a closer look at the charging process using a parallel plate model. When the connections are made, electrons are pulled from the plate connected to the positive terminal and pushed onto the plate connected to the negative terminal. As shown in the diagram, one plate gains a positive charge, plus Q, while the other gains an equal negative charge, minus Q. This separation of charge creates a potential difference, delta V, between the plates. An important characteristic of a capacitor is that even after the battery is disconnected, the plates remain charged. Because the plates are isolated, the charge has nowhere to go, meaning the device effectively stores both electrical charge and the energy associated with the electric field between the plates. This ability to retain charge makes capacitors vital for applications requiring quick bursts of energy. To test our understanding, let us consider a quick quiz. Suppose a capacitor is storing a charge Q at a potential difference delta, V. If we replace the battery so that the applied voltage is doubled to 2 delta, V, what happens to the capacitance and the stored charge? The correct answer is D. The capacitance remains the same while the charge doubles. This is a fundamental concept in electrostatics. Capacitance is a geometric property of the device itself, determined by the size, shape, and separation of the conductors. It does not change just because you change the battery. However, since capacitance is the ratio of charge to potential difference, doubling the voltage must result in doubling the stored charge to keep that ratio constant. We can even determine the capacitance of a single, isolated conductor. Consider a spherical conductor with a radius, a. From our study of electric potential, we know that the potential, V, at the surface of a sphere is equal to the Coulomb constant Ke times the charge Q, divided by the radius, a, assuming the potential is 0 at infinity. By applying the definition of capacitance, which is the charge Q divided by the potential difference delta, V, we find that the Q terms cancel out. This leaves us with a capacitance of A divided by Ke, or 4 pi epsilon naught times A. This result beautifully illustrates that the capacitance depends strictly on the geometry. This case, the radius of the sphere and is entirely independent of the amount of charge or the potential applied to it. The most common configuration we encounter is the parallel plate capacitor, consisting of two conducting plates of area A separated by a small distance d. If we assume the plates are large relative to their separation, the electric field E between them is uniform and equal to the surface charge density sigma divided by the permittivity of free space, epsilon naught. Since the field is uniform, the potential difference delta, V, is simply the electric field strength times the separation distance, d. By substituting these relationships into our primary capacitance formula, we derive that C equals epsilon naught times the area A divided by the distance d. This formula shows that to maximize capacitance, you should either increase the surface area of the plates or bring the plates as close together as possible without them touching. We see the principles of parallel plate capacitance in everyday technology, such as computer keyboards. Many keys operate using a movable upper plate and a fixed lower plate separated by a flexible insulator. When you press a key, you are physically compressing that insulator, which decreases the distance d between the two plates. Referring back to our formula, where capacitance is inversely proportional to the separation distance, we can conclude that decreasing d causes the capacitance to increase. This change in capacitance is detected by the keyboard's internal circuitry, which then registers the key press. This is a practical example of how changing the physical geometry of a capacitor directly affects its ability to store charge. Now let us look at a more complex geometry: the cylindrical capacitor. This consists of a solid inner cylinder of radius, A, and a coaxial outer cylindrical shell of radius, B, both with a length, L. To find the capacitance, we first determine the potential difference between the cylinders using the electric field of a line of charge. The potential difference is proportional to the natural log of the ratio of the radii, B over A. By applying the definition of capacitance and using the linear charge density lambda, we find that the total capacitance is the length L divided by 2 Ke times the natural log of B over A. We often express this as capacitance per unit length. A common real-world application of this design is the coaxial cable, which uses this geometry to shield electrical signals from external interference. Similarly, we can calculate the capacitance for a spherical capacitor, which consists of an inner sphere of radius, A, surrounded by a concentric spherical shell of radius, B. The potential difference here is found by integrating the electric field from the inner to the outer conductor. This results in a capacitance formula of the product of the radii, A times B divided by Ke times the difference, B minus A. An interesting mathematical check is to see what happens as the outer radius, B, approaches infinity. In that limit, the expression simplifies back to A divided by Ke, which is exactly the formula we derived earlier for an isolated sphere. This confirms that an isolated sphere can be thought of as a spherical capacitor, with its second conductor located at infinity. To represent these components in practical engineering, we use standardized circuit symbols. These symbols allow us to create simplified diagrams of complex systems. A capacitor is represented by two parallel lines of equal length, which visually mimics the parallel plate model. A battery is shown as two parallel lines of unequal length. The longer line always represents the positive terminal, while the shorter line is the negative terminal. Finally, we have the switch, which can be depicted as either open or closed. An open switch indicates a break in the circuit where no current can flow, while a closed switch indicates a completed path. In this text, we use a color coding convention where capacitors are blue, batteries are green, and switches are red to help distinguish between them. In summary, capacitance is a fundamental measure of a device's ability to store electric charge and energy, mathematically defined as the ratio of charge to potential difference. The most important takeaway is that capacitance is a purely geometric property. It is determined by the shape, size, and arrangement of the conductors, not by the amount of voltage you apply. For parallel plates, capacitance increases with area and decreases with separation. We have also seen how specific formulas are derived for isolated spheres, cylindrical coaxial lines, and concentric spheres. Using standard circuit symbols, we can now begin to visualize how these components interact within larger electronic networks to manage and store electrical energy. To wrap up this lesson, here are 2 review questions to test your conceptual and mathematical understanding. First, consider the parallel plate capacitor. Why does the capacitance increase when the plates are moved closer together? Try to explain this by thinking about how the change in distance affects the electric field and the resulting potential difference for a fixed amount of charge. Second, perform the mathematical derivation to show that the spherical capacitor formula reduces to the isolated sphere formula as the outer radius approaches infinity. Practice rearranging the variables and applying the limit to see how the geometry simplifies. Working through these exercises will help solidify your grasp of how physical dimensions dictate electrical behavior.